I'm not going to go into much of a bio. As Joe said, I'm from our St. Louis office. Subsurface Constructors, we're a 115-year-old geotechnical contractor, been doing ground improvement for about 15 years. And that's kind of what brought us up into this area. We're doing a lot of ground improvement type work. My background is geotech consulting earlier in my career. I have a bachelor's in geological engineering from, if you've ever heard of University of Missouri Rolla, now it's Missouri S&T. Joe gives a thumbs up. He must know a little bit about it. Maybe he went there. And then a master's in geotech from University of Illinois, another Big Ten school for you, University of Minnesota fans. But I'm going to get right into this presentation, what I call Vibro ground improvement for St. Louis Ice Center and the St. Louis Blues practice facility. So it's got a lot of appeal in the St. Louis area in particular because it is the St. Louis Blues new practice facility, at least new as of about fall of 2019. Of course, this isn't working. Here we go. Anyone? No. There we go. Look at you. We've got tech savvy people in the room, which is helpful. So when I'm pretty active in our geotech group in St. Louis, and we put on a lot of these types of events, whether it's dinner or conference. And I'm big on not just showing up to present. I want to bring something somewhat unique to the table. And we do a lot of ground improvement work, but a lot of it's pretty similar, not really that complicated, straightforward. But this one in particular is interesting in that it's multifaceted. So I'll talk a lot about, we do a lot of ground improvement for bearing pressure, settlement criteria. This one also has a liquefaction mitigation component to it, which makes it particularly challenging because you're designing for a couple different approaches, which in the Midwest is not that typical. You know, we've been doing ground improvement for about 15 years in St. Louis area. We've probably seen, you know, maybe 10 liquefaction type jobs in that time frame. So it just doesn't come up that often. And there's some unique challenges, or at least I would say necessarily unique, but challenges on this project that I think from a geotechnical component or perspective are interesting. And so I invite you to, you know, hopefully you can follow close enough when I'm showing borings and CPT logs and things like that to get an idea of, you know, really what we want to do on these jobs is have a feel for what's going on in the ground. You know, are we accomplishing at the end of the project what we set out to accomplish? And that's not always 100% straightforward. And that was the case on this particular project. So talk about the structural components of the project, or at least what it is they're building out here. The geotechnical components, soil mechanic, or the soil stratigraphy, of course. You know, and what the recommendations and desired outcomes were. I won't spend a lot of time going into a lot of detail about Vibro ground improvement, because I feel like most people probably have seen this sort of thing, you know, in the last few years, but I will go into it enough to where if you haven't, hopefully you have a better understanding. As I mentioned, there's some challenges on the project. You know, it wouldn't make a very interesting case history if the contractor, it's always more interesting when the contractor runs into problems, right? So everybody else wants to see other people's problems. The problems here weren't great, like we have a lot of them, but to me, from a geotechnical perspective, they're interesting. And so hopefully we can all gain something from that, whether it's you just learning a little bit more about ground improvement. You know, we as a contractor certainly learn more about our capabilities and what we can do in certain soil conditions through this project. So we say St. Louis Ice Center. It's actually about 20 miles northwest of St. Louis in a suburb called Maryland Heights, Missouri. If you're familiar with St. Louis, Missouri at all, you get on Highway 70 and go pretty much straight west. You know, map-wise, it's northwest. You go right through the Missouri River floodplain. So for those at home, well, even here, laser pointer-wise, it's up here, but those at home looking the upper left corner, you see the Missouri River come through there. This is on the St. Louis County side, and that's all river floodplain. On the St. Charles County side is basically bluff and not so much floodplain. It goes up pretty quick. And so if you're looking at this on aerial, you see kind of right here in the middle, the red mark is the site, Maryland Heights, Missouri. But what I like about this particular Google Earth view is that it shows other projects nearby. And if you look towards the top of the screen, the Ameristar Casino project. That was a casino built probably 30 years ago, and then they had an addition about 15 or so years ago. Hayward Baker actually did some ground improvement on that site. So right up here, and that was for some liquefaction mitigation. Now, just on the other side of the highway, people at home can't see my laser pointer, but where it says South 5th Street, that's a huge development called Streets of St. Charles. So it's like traditional mixed use, apartments, parking garage, movie theater, office building, and all of that is on ground improvement that we did, but it's all for bearing pressure and settlement. So that sits high up on the bluff, and there's no liquefaction concern on that side of the river. On the St. Louis County side, where you see Maryland Heights, again, liquefaction mitigation came into play. And just for reference, next door to our side is a Hollywood casino. That particular structure, the original casino structure, is on driven concrete pile, and the parking garage part of that development is on auger cast pile. And that's kind of that structure is probably about 25 or so years old, and that's really pre-seismic design. You didn't get into a lot of seismic approaches to the project 30 or so years ago. It was just deep foundations. So if that same structure was built today, those foundations might go deeper if you're worried about liquefaction. So let's get into a little bit about the development itself. So again, the St. Louis Ice Complex, this is a multi-use ice facility. Be a lot of, so 4 rinks ultimately, one of those being outdoor, 3 of the rinks are inside, so inside structure, and then office building component to that as well. And in terms of sequence of construction, we worked on the main building with the 3 rinks and the office building first, and then they were kind of toying with what they wanted to do on the outside rink. Ultimately, they built that about a year later. We did ground improvement for that as well, but you'll see that here in a second in a graphic. So a large development. Again, St. Louis Blues practice facility, but the main use for this is going to be youth hockey tournaments. That's going to be, there aren't a lot of sheets of ice in the St. Louis area, so this is going to be kind of taking over as the main location. The project team, St. Louis Legacy Ice Foundation, so there's a Blues ownership component to that. City of Maryland Heights, Missouri, maybe some other folks there. We worked for Arco Construction as a design build contractor, headquartered in St. Louis. Neely Engineering was a structural engineer, and geotechnology out of St. Louis was a geotech. And I guess one other mention is that what was nice as a subcontractor, geotechnical contractor working with this team in a design build capacity, is that we were involved so this particular site was obviously chosen, but about a year before that was chosen, they were working on another site a couple miles down the flood south in the same floodplain. That site fell through, but we were kind of going through multiple iterations of what's liquefaction mitigation going to look like, what's ground improvement going to look like, what are our different options on the site, and that team worked together really well in that capacity. The main thing, the hard stop, was fall of 2019. So all this building had to be open by fall of 2019. Ultimately, it was 2 months after the Blues won the Stanley Cup. So it had a little bit more excitement associated with the opening than maybe what it otherwise would have. They won the Stanley Cup in the summer of 2019. So a little bit more excitement to it in that regard. This is an isometric view of the structure. So for those viewing virtually, that upper left-hand structure is the outdoor part that was done about a year later. Looks a little bit different. What ended up getting built is a little bit different what's shown here. It's still a sheet of ice, but in the far upper left-hand corner, there are some pretty large grandstands up here, and that's also an outdoor concert venue. I actually bought some concert tickets this morning for a conference or concert in the fall that's going to be held there. So multi-use ice complex concert facility outside. Most of what I'm going to talk about today are all the enclosed inside structures. So you have 3 sheets of ice, kind of in the center. At the top is the great big one here, sheet of ice here, and this is more of like your main entrance and on office building type, kind of more of a common area as you enter the facility. And so I guess one other thing to point out, well, I'll wait till the structural plan. So keep in mind what that looks like, and then we'll look at the foundation plan in a second. This is a statement that as a ground improvement contractor, we see every day, multiple times a day on projects all over the place. Hey, we need 5,000 pounds per square foot under your continuous and spread footings. So we're very, very used to seeing this with what we call aggregate piers or stone columns. Those terms are used interchangeably. What makes this a little bit more unique is this particular comment on the structural plan, and that is site class F mitigated to seismic site class D with stone piers. So stone columns, stone piers, aggregate piers, call them what you will. We have to put a whole bunch of compacted stone in the ground to achieve a seismic site class D. Now, the only thing I want to point out here is that I kind of question is that the geotech report didn't specifically say, hey, this is a site class F. So I'm not exactly sure where they came up with that, but they do clearly say, once you do ground improvement, we can use a seismic site class D. So I don't know if it's just inferred that it was F before, but the report really doesn't say that. However, it is clear that ground improvement has to be done to mitigate for liquefaction. So I'll go into a lot more detail on that. But going into a little bit more on the soils on the site, as I mentioned earlier, Missouri River floodplain. No matter where you are on the St. Louis County side of the river, there's Chesterfield, this is Maryland Heights. It's all pretty similar. Alluvial floodplain, you have, I say 4 to 12 feet is what this site showed. We always say 10 to 15 feet of called a clay blanket. It's not really, 100% clay. It's silty clay. It's clay silt. Some high plastic, but I think most of it's low plastic clay because it's got a pretty good amount of silt in there. Nevertheless, you have a clay blanket over sand. And the sand is loose to medium dense initially and gains in density and coarseness with depth, ultimately going into gravel and so forth. And so it's really about the upper 40 to 50 feet-ish that's loose and needs to be densified in a liquefaction scenario. On this particular site, we had way more CPTs than we had borings, and that's not that typical for the St. Louis area. CPTs, when I started my career, late 90s, you didn't see CPTs on any job ever. Now there's some companies there locally that have them, and we see a lot more of them. This was probably done about 5 years ago, this exploration, and it had, I think, about 15 to 20 CPTs, but only 6 borings. Only 3 of those borings within the footprint of a 300,000 square foot structure. So that was pretty different to see in a report in the St. Louis area anyway. And only one of those borings went to 60 feet. I think the other 2 were 25. 2 CPTs were pushed deep, 190, and one I think was 106. And then just, an extra thing here, the site required about 5 feet of fill to get to just below finished floor. So just some things to keep in mind. Moving along, the structural foundation plan looked like this, and I know here you can't see it really well. Hopefully you can see it a little bit better if you're close to your screen at home. But all these square footings and your continuous footings, all these footings here, lower right-hand corner, all those squares require 5,000 pounds per square foot. So that note that I pointed out, they're saying 5,000 pounds per square foot, inch total, half-inch differential on the settlement, and seismic site class D, or I'll get into the specifics on the liquefaction recommendation in a second, exactly how they defined the treatment zone for that. They meaning the geotech consultant. So here you see the boring, and hopefully see that the borings and the CPTs. So as I mentioned earlier, borings B1, 2, and 3 are the only ones that are within the footprint of that big development. B4 just outside of that outdoor rink, so pretty close. But otherwise, you just had CPTs to go on this side. I'm kind of more, I like to know what like somebody to classify what they saw. So this boring B2 is very helpful. I'm going to refer to this spot right here, this C10 and B2. That's literally only place in this entire development that had a boring and a CPT at the same spot. And I'm not at all critical of the plan, but it kind of ultimately, and you'll see how you make a recommendation on liquefaction on worst case scenario or a summary of site. And what you find is a contractor explaining these things at all these different points is in some places it's a lot better. They're trying things that aren't really achievable because it's already pretty good. So we'll go into some detail on that. But keep in mind that C10 and B2 right in the site. And generally speaking, this is a alluvial floodplain. So it's not like drastic changes across this site. It's generally all pretty similar. So this is that C10 CPT. Just a couple things to point out is that, as you see here at the very top on the soil depiction, cohesive type material about 10 feet, and then it gets into granular. And there's a lot of silt classifications in the CPT. If you look at the boring, there's not much silt in there. It's predominantly sand, and I'll show you kind of what they did find with silt. But this is a case where if you don't have a lot of actual soil samples and you can't do grain size analysis, and that becomes an important component when you're doing the type of ground improvement that we were doing out here. But even on this particular CPT, a couple things I'll point out is that if you look at the correlated SPT from the CPT data, which I kind of, again, old school, like to go to that SPT correlation, and at 10 feet, it gets to be over 20, maybe the equivalent of that be over 20 blow counts. That's probably not going to liquefy. That's pretty good sand. And then you get into some weaker zones, and then it kind of peaks out again at about 25 feet. And then another lower zone, and then about 35-ish, 37 feet is where it just goes through the roof. And so that's the density of that sand in that area. And in an analysis shows that a lot of that is liquefiable. Not all of it, but in zones. So this is the soil boring right next to that. The only place we had on the site that is soil boring right next to the CPT. And so it agrees with the CPT, SPT wise, because right at about 10 feet, have an 18 blow count location. And then at about 25 feet, a 17 blow count location. So you're seeing those denser areas separated by looser sand. Now, one thing I call out here is this silt layer. I question that. I mean, and as a ground improvement contractor doing Vibro, I'll get into the details of why this is important. But the more silt that's in that boring, the less likely that we can show a significant amount of improvement with Vibro ground improvement. And so you want a very small amount of silt and show a huge amount of improvement in the sand. So the silt percentage becomes important. And so you look at right about 14 feet, you have 4% passing the number 200. We know we can compact the heck out of that with Vibro. If you get above about 10%, 10 to 15%, then it becomes less likely that vibration alone is going to improve that soil. So you look at this layer that shows 5 feet of silt. How do you really know that, though? You have an 18-inch sample you're pushing right here. You don't know that that's 5 foot thick. Maybe it is only 18. But it's still good to know that somebody could put eyes on that, visually classify that as predominantly a silt-sized material. So it's all helpful. So get into the liquefaction analysis and the geotech report. The design event became a 7.7 magnitude earthquake, and they describe there are 2 fault zones, design fault zones, if you will, in that neck of the woods. So that most people have heard of the New Madrid fault zone. It's in southeast Missouri, about 120 to 150 miles away from this site. There's the Wabash Valley one that's along the Illinois-Indiana border. That's also about 150 miles. The only actual evidence of earthquakes in the New Madrid were 1811 to 1813. There were 3 major events that history shows, like analyzing sand boils and things like that, that those magnitudes range from 6.8 to 8.1. So pretty massive earthquakes. I mean, it's reported in books that Mississippi River flowed backwards during that time because of the earthquake. If you're familiar at all with the geology, there's a place down there called Reelfoot Lake, real big for bluegill fishermen and duck hunters. Reelfoot Lake was formed when the river supposedly backed up and went into like channels and so forth. But that's a huge lake to this day. So anyway, some major events that happened, a long time ago that helped lend credence to this 7.7 magnitude earthquake, which ultimately is 2% exceedance in 50 years. So big event. a criteria defined and analyzed in the report was this liquefaction potential index. And so that is basically a measurement of risk to damage of foundations from liquefaction. So it's not just taking a small zone in a boring and saying, hey, this is going to liquefy. It's applying that to the entire soil column and saying, assessing the risk of damage to the foundations. And so they did there's a couple different softwares used. One that took the borings into account, one that took the CPTs into account. So these were two separate ones, but between the 3 borings under the building footprint, 15 CPTs under the building footprint, they developed what they call, again, a liquefaction potential index. And so out of those 18 locations across the entire site, the worst case scenario on this liquefaction index was a 7. Well, if you look at the range of what that means, high is 5 to 15. So even the worst case scenario on this site was not super high for liquefaction. As a matter of fact, the average was in the low risk of damage from liquefaction range. And I think that this, not that I was necessarily in the room between the geotech consultant and the owner, but there are some things that you might question from a geotech perspective that was not recommended and done ground improvement wise, but you kind of start to understand that this site wasn't horrible in terms of what could potentially happen in an earthquake. Matter of fact, a 7.7 earthquake, the ice arena would be standing in this area and everything else would be in shambles if you know this area. Nobody's going to the ice arena to play hockey after a 7.7 magnitude earthquake because there aren't any roads you can drive on in that area. But anyway, an idea of what the criteria were here, at least from an analysis perspective of the borings and CPTs. Those same borings and analysis showed that the post-liquefaction settlement could be anywhere from 2 to 8 inches. Now, again, this is analyzed per boring and CPT location. So one CPT shows, well, post-treatment liquefaction will be 8 inches over here, and over here will be 2 inches with an average of roughly 5 inches. And all that settlement's going to occur pretty much in that 7-foot to 37-foot range on that soil profile. So ultimately, the geotech report recommended to the structural engineer, hey, you can use seismic site class D if somebody does some ground improvement down to about 35 feet, which ultimately became closer to 40 feet because you're assuming that there's 5 foot of fill that needs to go across this site. So again, important to remember when we show like the treatment depths, that the goal from what we assumed working elevation would be, we're trying to get to about 40 feet for ground improvement. So again, just to reiterate the design requirements, 5,000 PSF design for the footings, which results in an inch total, half-inch differential settlement, liquefaction mitigation down to 35, or again, 40, depending on how much fill went in, and post-treatment liquefaction settlement 2 inches. So keep in mind, these are two completely separate design approaches. You design for bearing pressure, trying to achieve a higher bearing pressure in that upper clay blanket that the footings would be sitting in or above and fill. And keeping that settlement analysis to an inch total between footings, half-inch differential between footings. And then your liquefaction settlement is something completely different. We've had a seismic event. We want to make sure it doesn't settle more than 2 inches after a 7.7 magnitude earthquake. So this is where we get into the kind of like little, at least up for discussion in terms of the approach. So there was no recommendation for treatment under the ice slabs. So you're talking about a pretty massive area, 4 slabs of ice out here. None of it has ground improvement immediately under the ice. It's all the structure around the outside. And so the thought process there was structure is going to be fine. It's not going anywhere. We've treated under it all over the place. If the slab cracks and all that, we have to replace the ice. We're good with that. That was kind of the owner's ultimate risk assumed. And additionally, and this would kind of surprise me in my involvement, they didn't really require any post-treatment SPTs. Normally, when we're treating for liquefaction, we have to go back or, hire a geotech company, go back, drive some spoons, put some CPTs and verify this improvement that we've done across the site, but that wasn't required here. So we'll go off a little bit of a tangent here just to kind of describe quickly what Vibro ground improvement is, if you're not otherwise familiar with it. Most of the work, that probably 99% of the jobs we do are with these rigs that we show here. Certainly this tool goes with all the different ways we install stone columns and do ground improvement. And this is what we call a Vibro flot. So there's a eccentric weight that rotates around an axis really fast inside of that tool, causes a very high frequency vibration. If we're standing from me to that table, you really can't tell it's vibrating. So again, pretty high frequency. We can flush air or water through the nose, and most jobs we're just have compressed air going through because we're in clay soils oftentimes, and the air just helps you get the tool out of the ground easier. However, this project is different where we're using a water flush. So it's a little bit different animal when you're using water through the end of the tool. I'll get more into that. And these can be either hydraulically or electrically powered. Our Vibro flots are hydraulic powered. One thing I'll point out here is this particular setup, that's a trimmy that's welded to the outside so we can bottom feed the stone. I'll show you what that looks like in a second. But again, most of the projects, and even this, the bearing pressure component of this project is that we're using a stone column or a series of stone columns under a footing to provide a higher bearing pressure than what the existing soil was capable of. So oftentimes in a geotech report, they say, well, the soil is good for 1500 PSF, but structural engineer wants 5000 PSF, or maybe wants to size their footings around that higher bearing pressure. And that's where aggregate piers or stone columns come into play. In terms of installation, again, going through this just kind of quick. We can do a dry top feed where we're either pre-drilling a hole or in soft clays, just jamming a tool in the ground, taking the tool out, dumping in stone in lifts and compacting it again with vibration and down pressure. If we're in a more collapsible soil, I showed you that, kind of highlighted that trimmy. If we're worried about collapse, we can just bottom feed the stone. So we're pushing the probe in the ground, pushing stone through it, and just raising it up just in little lifts to let enough stone out that we can compact it, not worry about losing the hole. And this project required what we call a wet top feed. And there are reasons for that. So I'll touch on it in a minute. It has to do with what our equipment can do, but also the types of soil that we're in, sands, silty sand below the water table. So a lot of what we do are what these mast attachment rigs where the Vibro flot's attached to the mast. We have crowd pressure. We can push it into the ground with a lot of force, open up a hole. On this particular site, you don't see any drills out there. We're not pre-drilling anything. We're just pushing the probe in the ground, taking it out, and it leaves an open hole, dumping in stone. Alternatively, we have a mast system on excavators, same type of deal. We're just forcing the probe in the ground, dumping in stone. We can pre-drill, you know, if we're in a pretty dense layer we have to go through, or we do a lot of work in fill soils that have obstructions and that sort of thing, you do have to pre-drill through that material. But the main reason we're here today is to talk about this particular technique. And so these other rigs, I'll back up a slide. This rig and this rig are only capable of going down about 30 feet, 30, 31-ish, 32 maybe at the most. But when you have a job that's requiring liquefaction mitigation down to 40 feet, well, you have to have something that can get to 40 feet. In this particular case, we use cranes, again, vibratory tools, and we're jetting water through the end of that tool that helps advance it. We don't have that down pressure force capabilities with this particular setup. So what does that mess looks like? It's logistically difficult with water. To work very close with the general contractor to control the water across the site, because if they just let it pool, we'll literally be working in a pond. And so it's important to try to direct the water away from the operation and reuse it. I'll show you how it worked out fairly well here, and because we were relatively close to the Missouri River, that was a good thing. One, I want to say limitation with wet top feed Vibro, but if you've heard of the term Vibro compaction, you're using this exact technique, but Vibro compaction is reserved for improvement of sands when you're not putting, you don't have to put any additional stone in the ground. You just send the tool in the ground, compact loose sand, and you can get huge improvement out of it. However, as I mentioned earlier, if you get above about 10% fines, you're going to start to struggle with seeing an improvement in that soil. And there we're putting stone in the ground in those cases. So you get the reinforcement mechanism of the stone in a finer grained soil, or at least some percentage of fine grained soil. And so, although I showed you a soil profile that only showed a 5-foot layer of silt, we only had 3 borings across the site. If you look at the CPT, it's assuming that some of that's got silt in it. We don't really know. So we're putting stone in every single hole all the way down to maximum depth on this particular project. And this is just a quick graphic depiction of wet top feed. Again, we're jetting water, and so the water and vibration helps open the hole and helps keep cuttings out and keeps the hole pretty wide, significantly wider than the Vibro probe itself. And then you're just dumping stone in from the ground surface. Hopefully the folks at home and actually here, we're not going to sleep too much. This is a slide that might lend itself to some slumber, but I'm going to talk about it anyway, because I think on this particular site, it's worth noting what we're trying to accomplish in the ground. And so in this illustration, the yellow is sand, the dark yellow is compacted sand, and we are trying to, because we can improve the sand, that bearing pressure is shared a little bit more from the adjacent soil. So you show a pressure distribution across the top, and you see that that curve isn't quite as high as it is here in a clay soil. So in a clay soil, we're not really improving that clay soil very much. We're reinforcing it, and we're relying more on the column itself to provide that increased bearing pressure. So on this particular project, we have both of these things going on. We have the compacted yellow, the dark yellow, below that clay blanket, which is what you're improving for liquefaction mitigation. And then that right graphic is what we're improving the cohesive soils for a higher bearing pressure so you can put footings on top of it. So hopefully that makes sense. So this is our, I'm just kind of talking about the main building structure, not the outdoor rink here, since that was the first phase of the work and the biggest part of the work. So this is our design. You see a whole bunch of black columns on there, and those are black circles. Those are all the treatment points locations where, again, trying to get 5,000 PSF, trying to treat down to about 40 feet for liquefaction, just doing a quick time check. And for the most part, this site went as planned. And so if you kind of look at the grid of, or the rectangle G and K, keep an eye on that because I'm going to talk about that specifically. All the other grids, we pretty much went down to the depth that we tried to on all those locations. But I'm going to talk about G and K because that was a little bit more difficult, or at least on the surface, when you first look at our treatment depths, you're like, you know, these guys aren't going as deep as they're supposed to. What's the problem? And so the problems are more fun to talk about in these settings, at least for folks like yourself. If you're the contractor, they're not as fun to talk about. But ultimately, we all could wrap our head around this and feel pretty good and sleep at night that we improved the heck out of this site. So I'll zoom in a little bit on, this is that G location, just so you kind of see the treatment points a little bit better. I think we ended up doing about 800 and some points across the first phase of this project, those 3 rinks in the office complex. So that's just a closer up depiction of the design. And this is the detail. So you can't really see in the foundation plan all those different footing sizes, but these are all the footing sizes that we had on this job. And so some things worth pointing out are those big footings. These stone column locations are really close. And the reason that is we're trying to get 5,000 pounds per square foot in a relatively soft clay blanket. And so to do that, you have to space these things pretty close. You have stone columns that are 4.5 feet on center in some cases, using a diameter of about 28 inches. So that works really well for bearing pressure. But when you're trying to get a vibro flot in the ground to compact sand, and you've done this a couple times in one area, it becomes a lot more difficult to get the vibro tool back in the ground because you've put these things on such close spacing. So the whole bearing pressure in clays scenario did not always agree with the liquefaction treating scenario in terms of trying to get to that design depth of 40 feet. So just a picture of the crane setup here. Go through that. Again, as I mentioned, very sloppy site. I'll show you this 1-minute video at the end. You can see really how sloppy it is as well. You're just pumping water like crazy into all these columns. But it was controlled fairly well on this particular site. And again, dumping rock from the ground surface into that open hole. So when we talk about water, I don't really have a good measurement or description of the distance. But if you look on the right side of the picture, kind of the middle to right and the far right, those are water tanks where we were storing some water. We were pretty fortunate here. We could use, you know, in a lot of these types of jobs, you have to truck water into the site. And for 820 some points, going down to 40 feet, that's a huge amount of water that you're having to go through. I mean, I don't know if this was the case here, but I've often heard 10 to 15,000 gallons of water a day is what you might go through on a vibro compaction job. So if you're trucking all that water in, that becomes a logistical and cost nightmare. On this particular case, we benefited from this. If you're looking at this screen at home, it's the far left. So here is the borrow pit, and they dug that out right away. And once you get through that clay blanket, the Missouri River is supplying all the water you need. So that became a great benefit to us. Now we had to pump it a really long way. So go back to these pictures. You look here where the cranes are set up, and that far right tank, that's probably, I would guess about 150, 200 yards. And then here you see that same far left tank, and on the far right-hand side of the screen, you see a pump that's on the edge of the borrow pit. So we're talking about probably 400 yards, 500 yards of distance from the borrow pit to the actual equipment where we're trying to run this. You got to pump it a long way, but it's still better than trucking it in. Is there anything else I want to point out here? I guess, let's see. So as I mentioned earlier, we're going to focus on that area G and area K. And the reason why is because we were not getting the depths that we wanted in some of the treatment points in those locations. And so if you look about the center of your screen, CPT C6, keep in mind about where that is. And then CPT C14, we're in those two grid areas of G and K. And I'll show you what those CPTs look like. So I liked the idea of using this. It kind of looks crappy from a presentation standpoint, but I thought it was a good way to show, okay, what's going on during construction here. And basically this is our project manager's plan where they're just highlighting and writing in what we did across the site. All the green locations are where we hit the depth we were trying to hit. So 40 feet or greater at all the green locations. The yellow ones, not so much. So you'll see the numbers next to the yellow locations are we're hitting something less than 40 feet. And so you start to look at this kind of close, 36, 38 feet. Nobody's really too worried about that. You're getting really close to that. You know, you can argue how much fill was placed on site before we showed up. You know, again, the geotech report said 35 feet. We're hitting that here, depending on how much that fill was out there when we started working. But if you look at that big footing that has 9 stone column locations, you know, you only hit 22 feet here. Well, when you're trying to hit 40, 22 is a problem. And here you hit 30. If you're looking at home, you see 610 and 556, those numbers, 30, 28. You know, that's getting to be where the geotech starts to question, hey, are you guys really doing what you're set out to do? And we are too. We're questioning the same thing. Well, okay, what happened? What's going on in those locations? Can we be doing something different? Let's take a closer look. And so the closer look, and hopefully you can see this, is that, again, when we design the job, you're designing off a worst case scenario. Probably the worst CPT on the site is what you're really kind of going off of. Where if you look at the CPT real close to this treatment location, at 10 feet, the strengths go through the roof. Well, maybe not through the roof, but it's correlated blow counts of way above 20. Talking about 25 area, that's not liquefiable soils. And when the probe hits that, it's going to densify it even more and have a really tough time advancing through that. So that's one thing that could be going on. If you look at the big footing in the upper right-hand corner, you have 9 treatment points, all relatively closely spaced. So I don't really know the sequence of construction on this particular footing, but if I had to guess, I'd say we started on the right side of the footing and we moved our way to the left side of the footing. And the reason I think that is because we had a much tougher time getting depth on the left side. So that tells you you're improving the heck out of that zone. Now, if this was a liquefaction mitigation job that required liquefaction mitigation across the big mat, our spacing would never be as close as it is under these footings. We'd have probably 6 to 8 foot on center would be my guess between treatment points, and that would be sufficient to densify everything. But because we were trying to get bearing pressure at 5,000, we have these things very closely spaced, and you're compacting the heck out of the ground there. So you're going to have a tougher time. One, because it's already not too bad. Like really the correlated SPTs are 20, maybe you got 18 or something here, but 20 or above from 10 feet all the way down. So you would suspect to have some trouble advancing a vibro probe through that material. And so this is how, you know, you start to talk to in a team setting of a project, say, hey, this is what's going on. This is what we think is going on. Is everybody okay with that? Now we have a whole bunch more yellow down at the bottom part of this K grid. And this one, you know, a little bit more of, okay, maybe we should do some extra improvement. We have some points where we're able to hit 42, 42, 41. You know, all the green points we're able to get to depth, but a bunch of points in between we're not. You can't see that this, you know, huge yellow in here where 32. You know, so there are some areas where we ended up going back and doing a little bit of extra ground improvement for liquefaction mitigation. We're fine with what we're accomplishing from a bearing pressure perspective and getting that stone in there and getting it compacted. But just for comparison's sake, you know, again, you pull up the closest CPT and say, well, what's the soil like exactly at that location? And could that be indicative of what our response is to the vibro flop being in the ground? And this one's a little bit more sporadic and a little bit more on the lower end, you know, so you're pretty much, you're a little bit lower here. And then again, about 20 feet from about 15 or so down to about 23, 24 feet. You know, that's an area where you definitely have to treat. But then again, above 25 feet, you're still in really non-liquefiable soil. So I just like to point these things out because, you know, again, when the initial look is that, hey, we're not getting down the depth we need to, start to look at a little bit closer and think that, well, okay, we're getting a lot of improvement in a lot of these zones, maybe not so much in between. But again, we did do a little bit of extra treatment. So just a little bit of summary. You know, I didn't show you all the grids where we were able to hit 40 feet because that's no fun. See things that, you know, you did what you said you were going to do. I just think it's interesting to show, kind of get a concept of what's going on in the ground. When you send these tools in the ground, how is the ground responding to that? And be able to look at the borings and CPTs and say, okay, well, this one's got a little bit of silt, or this one's got a lower strength at this location, and look at what happened with the vibro and see how that matches up, and try to get a full understanding of, hey, did we accomplish what we wanted to from a liquefaction mitigation perspective? So as I mentioned, we certainly had some shorter depths in some locations. We treated a little bit of extra, and I don't think it was a lot, you know, a few extra points just to make sure. For the most part, though, the project team was satisfied once they looked at the specific CPT or boring close to those treatment points where we were getting shallower depths, and satisfied that that is no longer a liquefiable zone, or maybe it never was. You know, you're designing off of a CPT that's, you know, several hundred feet away and not necessarily right at that treatment point. So as I mentioned, added a few extra treatment points. But again, you want to be introspective as a subcontractor, and then obviously the project team. Okay, what are some of these reasons? I talked about some of them, but maybe even us. You know, we do lots and lots of ground improvement, but not lots of crane suspended vibro ground improvement where you're going really deep, because in the Midwest, you just don't see it that often. So is it on us? Is our operator not spending enough time trying to get that vibro down? Is it a mechanical issue? Do we not have enough vibration, not have enough power to the tool? I think we were pretty satisfied that ultimately that wasn't the case. Once you look at what's going on in the ground, we're treating so close in some of these zones and improving that soil. You have a tough time getting that flat in the ground after that. So kind of got ahead of myself there. So again, you're just compacting. This would look a lot different in terms of your ability to get that tool in the ground if these things were spaced farther, which they traditionally would be in a broad scale liquefaction mitigation job. You know, if they would have had us treat under the slab, we would not have had that problem under the slab because they're spaced out a lot more. But that bearing pressure requirement required the spacing to be pretty tight. So just go through a couple of job site pictures. I didn't get very many of the actual stone columns after they were complete. Here you see one lonely stone column there in the middle of the site. Contractor came in behind us and put some, pretty good layer of crushed stone in, then started digging the footings. I think this is kind of a cool pic that shows, that crushed stone they put on top is really tight material, able to excavate the footings, put those in, and just run through quick conclusions. This is somewhat redundant, but again, we're got multiple design facets going on. The bearing pressure scenario and liquefaction mitigation, which isn't always the case. A lot of times it's one or the other. So we tailor our techniques depending on what we're trying to accomplish, since we had to go to the crane mount, wet top feed. Mention the challenges. And again, an indication of, and we all have been there. When you can get on a project team where everybody can sit down and kind of talk through any issues, man, it's just so much better, in being able to do that. And Arco in particular has always been a contractor that seems to me like they have a good understanding of the geotechnical components and risk of a site, more so than a lot of general contractors that we've worked around, where they rely on geotechnical contractors to provide insight. And be part of the team. So that helped a lot here in determining what's possible on this site. We had been talking to them for, up to a year or two before construction started here. But that understanding, something as simple, seemingly as simple as knowing that Vibro ground improvement will not improve silty sand. It'll reinforce it, but it won't improve it. Those types of things are often lost on the engineering team. Like we see specifications, we're like, you're not going to be able to improve this zone. We can reinforce it, provide higher bearing pressure, but you're not going to be able to go outside of that zone and drive SPTs and show a huge increase in silty sand. In sand, for sure, but not in silty sand. And those conversations are important to have with the design team early on if possible. So this is where it could get interesting. I have a 1-minute video and you all should be fine. But when we tried all this, the people at home, hopefully we can make this work. Again, if this is on YouTube, so it's only a minute long, just shows a quick drone video of some work on the site. So what is my sequence again? I think I just have to pull that out. Well, hopefully that wasn't too bad for the home viewers. They were able to follow a little bit. If so, go to our YouTube page. That video is on there along with a bunch of other ones. Just kind of a cool drone video, I think, of the procedure. And click on the screen. Boom. And that's it. That's it for the presentation. I know for the Minnesota Wild fans, I had to throw in the logo, the Stanley Cup champions. Yeah, that was certainly an exciting part of working around this time at this facility. But I don't know if you all have questions. I see there might be 3 or 4 on the chat. We'll give first question anybody in the room that wants one, then we'll go. Yes, sir.
I guess have you done studies with CPT for the kind of range you're getting out of these things, the zone of influence with that compaction, the vibro compaction?
We haven't really done studies per se, but our experience is that at least with our vibro flots and the times that we've done this, I don't think our spacing's ever got more than about 10 feet. And the verification mechanism there is you're going, if you treat here 10 feet away, you treat here, you go right in between, or if you're doing this in a grid, you go in the furthest away point. And I want to say a lot of times it's around 7 to 8 feet on center is what we're comfortable with. Again, it depends on how dense that sand is initially, right? If it's really loose, then you're probably a little bit closer spaced.
And I have one more follow-up. Do you ever deal with large amounts of subsidence because of this? Is that an issue on this job?
It was not an issue on this job, but we're putting stone in the ground.
Yeah, that's
On every single one of them, putting stone. We have worked on a couple jobs where we had to bring in a bunch of sand just really for that purpose, just to make sure we're not getting too much heave. But that's a good question. You will get heave across the site. Heave in cohesive materials, subsidence in granular materials, just because you're going to drop that site. So a couple of projects we've done, you had like maybe a thin clay layer across the top. We'll just recommend they remove that thin layer, let us compact the site, bring it down, and then bring it back with more sand, compact it, come up. Sure. Oh, sorry. All right.
So maybe just a follow-up on that last, the zone of influence of your technology. You mentioned, I think, based on experience, it's sort of like 10 feet or something spacing that, or something like that. What was it on that big footing indentation that was been over penetration depth that you might have less than 40, 20, whatever it was? What was the spacing there?
So the question was, what's the spacing under the larger footings that I showed in that one grid, which was the area G, that one particular footing, but we had even bigger footings than that. And I found, it varies a little bit, but some are as close as 4.5 feet on center. So it's very, very tight. These aren't quite edge to edge, but they're close in some cases. And so, yeah, very tight zone. I don't remember what the 9-column footing was. I would guess it's roughly 15 feet on, 15 feet by 15 feet is the size of that footing. You're trying to get 9 points inside of that. It's pretty tight.
Lessons learned, it's easy to look back on this now, but going forward, you probably, even if you had to put nine stone columns in the ground, you might space them at 10 feet and end up a greater area, but you'd have same amount of time expenditure. You'd have all the numbers would work. Everybody would be super happy.
What wouldn't, okay.
I didn't understand that.
What wouldn't work in that scenario? So the add-on question was, could you optimally space those further because you knew you were treating the ground? So the important part to remember there is that we're trying to get a bearing pressure in the clay soils that footing is sitting on. So if you space those out too far because you're improving for liquefaction below that, you don't put them close enough to get your bearing pressure up to 5,000 PSF. You want to take an online question?
Yeah, first one was shear wave velocity measured?
They did a shear. Okay. So people there see that question, right? I didn't need to replace that or repeat it.
As long as they're looking at the chat box.
Okay. So with shear wave velocity performed in the CPTs, there was a shear wave. There was a shear wave velocity analysis done. It wasn't per CPT, but it was a specific site analysis of this site using time histories. Initially the method was ASC 710, but ultimately specific time histories of this particular site and how it compared to, I think they compared it to 6 historical earthquakes elsewhere in the world, and with a similar depth to bedrock response. So I don't know if I'm saying that perfectly because I've read the geotech report multiple times to try to answer a question like that. But as opposed to just using a theoretical method to come up with your seismic site class and ultimately a shear wave velocity number, they did a site specific study here and were able to get your peak ground accelerations lower than what the theoretical would have done. I think if they would have used the theoretical, they would not have been comfortable going to the seismic site class D even post treatment, or would have required a little bit different treatment mechanism.
Next one is, was there any validation testing done after the
No validation testing, with the exception of, so it's pretty common on, well, pretty much every project we do, or trying to provide a higher bearing pressure, it's pretty common to do a modulus test on a column. So we did modulus testing on the columns to verify the stiffness in the upper part of that column, but there was no post-treatment, deep post-treatment testing done to verify the liquefaction mitigation component.
And the last one online is 5,000 PSF bearing pressure considered typical? Is that
100% typical, with an asterisk by it. So I don't want people to leave this room and think, well, typical bearing pressure for aggregate pier stone columns is 5,000. And you go out and you drive spoons across the site and you get 30 feet away to hammer material and you tell us to give you 5,000 PSF, because it's not happening. So there are limitations, you know, as we put this stone in the ground and compact it, you have to have some resistance to that compaction, right? Zero blow count material doesn't provide any resistance to that. So you can't get 5,000 pounds per square foot. So great question. Important to remember. We see it in geotech reports every day of the week. Says a typical range of bearing pressures for stone columns and aggregate piers is 4,000 to 6,000 PSF. That's not wrong. That is a typical bearing pressure range, but doesn't mean we can get it on every single site. If you give me a 10-story structure and 2 blow count material, you're not getting 6,000 pounds per square foot. I can tell you that right now. So that's why we like to be consulted on these things ahead of time, in particular if it's borderline, you know, or really crappy. Because then you start to look at, you know, if it's might not be able to make aggregate piers work, you have to go to rigid inclusions, more of a grouted column type situation. Any else on virtual? Any other questions in the room? Yes, sir.
Yeah, the post liquefaction sounded showing back right there.
Well, I think if we didn't have the bearing pressure component, our treatment spacing would have pretty easily been further apart. So again, it's that, you know, the other liquefaction jobs we've done, we've never had to treat 4.5 feet on center or even 6 feet on center. We're able to spread that out a little bit more, knowing that once that tool gets into that sand, we can compact a pretty wide zone. You know, if the vibroflot's 20 inches big, then probably 5 feet on either side of that, maybe we can get a compaction, or 3 feet. So that's going to take it out further than what we had here along it, for sure along the spread. I mean, yeah, the spread footings, column footings, those are probably spread out far enough to where that spacing would have been similar if it was just for liquefaction and the bearing pressure component wasn't there. Yeah, Derek?
Yeah, it's just thanks for the presentation. You would pick out the layer of the sort of look at say some water pressure. Higher, see whether
You would have a really tough time knowing that in the Vibro installation. The CPTs, yes, like in most of the CPTs, if you look at them, they classify it as silty sand. You know, and that's why in you only had 3 borings. So you couldn't do that many grain size analysis if you only have 3 borings. You know, so that's where more borings would have become a little bit more handy to understand that. Ultimately, we approach this as putting stone in the whole thing anyway, so it kind of addresses everything. You know, if we were trying to be really picky about where we put stone, you almost can't put enough CPTs on the side or borings to really truly pick and choose where you want to put stone and where you don't. You kind of have to, yes or no, we're putting stone in the ground. And I think there was enough silt out there to assume that we were going to have to do stone. And, you know, there is some precedent for just using vibro compaction in the sand. And as you get into dirtier material, put stone there. So you have a compacted sand column where you're not putting stone in the hole, you're just compacting everything. And then as your fines content gets greater, you start putting stone in. We did another project in the Boot Hill, Missouri, where that's what we did. Here, I think there was enough silt, although again, few number of borings to be concerned, and just put stone everywhere. Sorry, I forgot to repeat the question twice. So if they haven't left, you know, they probably left by now. Turn it back to Netflix. Any other questions? All right, I greatly appreciate everybody being here. COVID times and all above. you never have a cold weather excuse up here in my mind. I mean, you guys got to function. I don't know how you do it, but you function in it. So you don't have an excuse not to show up because it's cold. But no, nevertheless, I'm appreciative of being here. And hopefully you got something out of it. Thanks.